Hello, welcome to m253 Calculus 3 here at Cañada College. My name is Lapuz and I'm the instructor for the course. In this video we will take a look at conservative vector fields and one of our big theorems in this course. The big theorem is called the fundamental theorem of line integrals. So let's first take a look at curves and regions to get us acquainted with a relationship between the two types of integrals, or the types of integrals that we're going to study. So curves and regions, just into the quick overview, a bunch of definitions here. The simple curve is a curve that doesn't intersect itself. A closed curve is a curve that starts and ends at the same point. And a piecewise smooth curve is a curve that can be broken into a couple of pieces or more, two or more pieces that are connected and smooth. In terms of regions, we're going to take a look at regions. Connected regions are regions that are make sure that they're attached. A simply connected region says that any points in there are going to be contained. Any line that we draw between a couple of points will be totally contained within your region. Or there'd be a path that would be totally contained in our region. Once we get to know a little bit about the objects that we're integrating over, we'll take a look at the functions that we're actually going to integrate. We took a look at vector or conservative fields. We studied vector fields in the first section, and then we kind of took a glimpse of a special type of vector fields called a conservative vector field, which requires us to find what's called a potential function. So remember that a conservative vector field is a special type of vector field that's a gradient of some other function that we're studying. So the other function that we're studying can be seen as a function of several variables whose gradient becomes a vector. And our task to find this special function is to go backwards. That is to say that if we're given a vector field, which is a vector of derivatives, can we kind of obtain the original function? So that original function, by the way, is called a potential function. And in this particular section, we're going to learn how to find a potential function from a given vector field for a given conservative vector field. And so now that we know how to find potential functions, the fundamental theorem of line integral uses the idea of potential functions. And what it says is that if you're taking a line integral of a conservative vector field over a particular curve, then all you really need to do is to evaluate the potential function, and evaluate it at the endpoints of your curve. So we could take a look at this as a fundamental theorem of calculus because it relates this integral with some sort of the derivative. It's a derivative in a different form. It's a gradient. And so we're looking at the gradient as a derivative, and integrating a gradient would essentially tell us that we're just going to evaluate the original function at the endpoints. And so that should sound really familiar in terms of the fundamental theorem of calculus that we learned. And what that also is saying is that it doesn't matter how you get from one point to the other point. The idea is that regardless of how you get from one point to the other point, if your vector field is a conservative vector field, all you need to do is evaluate at the endpoints. And so that is one of our big theorems for this chapter. And so again, the idea of a conservative vector field is important for us, and so we're going to need to identify it somehow. And not all vector fields are conservative, but we have a list of checklist of things that we can do, and these are all equivalencies. And so if one of them is true, then all of them are true, and if one of them is not true, then none of them are true. So this gives us a good idea of how we're going to figure out whether something is a conservative vector field. So if it's a gradient field, then it's conservative, or if there's a potential function that we can find, that's conservative, or if it's path independent with the line integrals, or in the zero in a closed curve situation, those are all equivalent. Now, it still does not give us a nice, easy way to find out whether something's conservative, because what we can do is we can use that algorithm and check if we can find a potential function. But we'll find a surefire way to check if a vector field is conservative when we learn more about taking derivatives of these vector fields with a div and a curl. Okay, so this is going to be our main check whether something's a conservative vector field. All right, so that is our overview, and I hope that helps.